Hello again and welcome to this lecture. This is the second part of statistics overview. Now, let's look at the notations that we use for statistics. Some general notations will make it easier to apply our methods and formulas to a wide variety of practical problems. So, the number of observations in a single sample, that we call it as the sample size or n, is simply the number of observations in one sample that we have. For example, when we say n is equal to 4, this is the sample of universities. For example, Seoul National University 1, Korea University 2, Yonsei University 3, and Sejong University 4. If two samples are at the same time under consideration, we may use n and m for both of them, or we may use n1 and n2. Given a data set consisting of n observation on some variable x, the individual observations will be donated by x1, x2, x3 to xn. The subscript here bears no relation to the magnitude of particular observation. So x1 here will not in general be the smallest observation in the set, nor xn shows the largest one. So given a data set consisting of n observation on some variable x, we can go for x1, x2, x3, x4. But this one is just an index. It has no relationship with the values here. Now, let's go back to our stem and leaf display again. We define that a stem and leaf display is a method of organizing numerical data. We have huge amount of data, values. This stem and leaf display help us to better understand our data. We can see the distribution, and also we can see what is the behavior of our data, for example, outliers. For example, we have a numerical data set, and for each xi consists of at least 2 digits, for example, 52. Then we say it is 5.2 multiplied 10 is equal to 52. So stem, leaf. In order to construct the stem and leaf display, first we select one or more leading digits for the same value. How? We identify the significant digits that will form the stem. For example, if we have 23, 25, and 29 here, so in here, 2 will be as the stem. Then we list possible stem values in a vertical column, and we arrange the stem in ascending order in a vertical format. So we will add our stems here. Then we record the leaf for each observation beside the corresponding stem value. We place each leaf in this side here. And then we indicate the units for stem and leaves somewhere in the display. For example, if you have 23, 25, 29, 31, 32, 36, 41, 42, and 47. So you can see these are one group, and one group. So we have 2, 3, and 4. Then we say 3, 5, 9, 1, 2, 6, 1, 2, 7. So this is a stem and leaf display. So the stem 2, 3, 4 represent the 10th place, and the leaf like 3, 5, 9 represent the 1st place. This method helps in visualizing the distribution of data efficiently. A stem and leaf display provides valuable insights into various characteristics of our data. It helps to determine the central tendency of or the most common values in a data set. It reveals how much the data values deviate from the central value, indicating the variability or dispersion. This scan shows whether there are any intervals in the data where no values are present, suggesting possible data discontinuities. It also helps us for visual assessment of how symmetric or skewed the data distribution is around the typical value. It can highlight any clusters or modes in the data, revealing where values tend to concentrate. And also, it helps identifying any outlier or extreme value that fall extremely outside the general pattern of the data. So let's see another example. The example says a common complaint among college students is that they are getting less sleep than they need. Average number of hours of sleep per day or over a 2-week period for a sample of 253 students is here. So we collected data and calculated the average number of hours of sleep per day over a 2-week periods of time for 253 students. So the stem here represent the first 5L. It means lower side. It means 5.5, 5.0, 5.1, 5.3, 5.4, 5.5. And 5H means 5.6, 5.7, 5.8, and 5.9, right? So we can have here, it means two digits we have here, 5 and 5. 5.6, 5.8, 5.8, 5.9, 6, 6.0, 6.0, 6.0, 6.1, the rest. So from here, we have a stem and leaf display. The first observation in the top row of the display is like 5 hours. This is corresponding to 5 and leaf of 0. So this is stem and these are leaves that we have here. And the last one is here 10.5 and 10.6. So the minimum value is 5.0 and the maximum value is 10.6. And we have the leaves also here. This display suggests that a typical or representative sleep time is in the stem of 8. Here you can see here. This is the highest sleep. And almost all students were getting between 7.5 to here, 7.5 to 9.5. You can see here. So you can see that even though we have 253 data, but using this stem and leaf display, easily we can understand, we can extract some knowledge from this data. Dot plot is another graphical or visual method for descriptive statistics. So a dot plot is considered as an attractive summary of numerical data when the data set is reasonably small or there are relatively few distinct data values. And in here, each observation is represented by a dot. You can see here. So each of these dot is one observation. We show them by a dot above the corresponding location. For example, these are the locations that you can see here. So when a value occurs more than once, there is a dot for each occurrence. And these dots are stacked vertically that we have here. As with the stem and leaf display, a dot plot gives information about location, spread, extremes, and gaps. So here is one example. There is a growing concern in the United States that not enough students are graduating from college. Here is data on percentage of 25 to 34 years old in each state who had some type of post-secondary degree as of 2010. So you can see here this data. Again, we have huge data and we show using a dot plot here. So you can see here, this is one outlier. What is this value? This is 68.8. Simply, we can see this is an outlier, right? Then we can see that the most of the data are Here, we can also see the average. For example, something like here is the average of our data set. So you can see that this dot plot also easily can represent the data for us, even we have many observations. Now, let's see how to plot histograms for discrete and continuous data. We have generally two types of quantitative variables, including discrete and continuous. A numerical variable is considered as discrete if its set of possible values either is finite or else can be listed in an infinite sequence. For example, we can count them. One in which there is the first number, second number, third number, so on. Then on the other side, we have continuous values. A numerical variable is continuous if its possible value consists of an entire interval of the numbers line, right? For example, time, height, age. For discrete variable, always results from counting. 1, 2, 3, 4, 5, something. However, continuous variables arise from making measurements. For example, meter, we can say 1, 1.5, 2, 2.5. Then again, between 2 to 2.5, there are infinity numbers. For example, 2.1, 2.11, 2.2, and many others, right? But in here, between 0 and 1, we have no number, or between 0 and 5, we have 1, 2, 3, 4, right? We can count them, but here, infinity. So for histograms, we deal with frequency. What is frequency? Frequency, the number of occurrence of a particular value or range of values within a data set. The number of times that a value occurs in the data set. In a histogram, the height of each bar represents the frequency or the number of occurrence, right, in a specific interval, or we call it as bit. For example, if a histogram bar corresponds to the interval of 10 to 20, then the frequency here is the number of data points that are from 10 to 20. Then we have another topic as relative frequency. This relative frequency represents the proportion or fraction of total data points that fall within a specific interval. How do we calculate the relative frequency? The number of times the values occurs divided by the number of observations in our data set. In a histogram, relative frequency is often represented by the height of bars relative to the total number of data points. So here is one example. If a data set consists of total 200 observation on X, for example, X is the number of courses a college student is taking this semester. And if 70 of these X values are 3, then we say, what is the frequency of 3, right? Frequency of 3 is 70. What is the total number? 100. 70 divided by 200 is 0.35. This is what? Relative frequency of value X. Number of occurrence for this interval divided by the total. In histograms, we can show relative frequency as percentage. So we can multiply relative frequency by 100. The relative frequency or percentage are usually of more interest than frequencies themselves. In theory, the relative frequency should sum up to 1. So we can multiply by 100 and we get it. For example, if the relative frequency of students taking 3 courses in college is 0.35, so if you multiply by 100, then you get 35%. In a histogram, percentage can be represented by adjusting the height of the bars to reflect the proportion of the total data. So this can provide a clear interpretation of the data in terms of percentage. Then we have something called as frequency distribution. This is somehow the arrangement of data that shows the frequency or relative frequency of different values or intervals in the data set. We make a table and we show everything in details. So once again, a histogram is a graphical representation of data, and the data is divided into intervals or bins on the horizontal axis, x-axis, and the frequency will go to the y-axis. We can go for discrete data and continuous data. For the discrete data, we first determine the frequency and relative frequency of x, then we mark possible x values on horizontal axis, and then we draw some rectangle whose height is the relative frequency that we have, right? So frequency, relative frequency, then we plot it. So I will show you example. Here is the example. How unusual is a no-hitter or one-hitter in a Major League Baseball game, and how frequently does a team get more than 10, 15, or 20 hits? So what do we have here? We have hits per game 0, 1, 2, 3, 4, 6, up to 27. So these are two tables. Then we say the number of 0 hits per game is 20. The number of 1 hit per game is 22, and so on. The number of 27 hits per game is 1. Okay. Then if you count the total number of these things, you will get 19,383. Okay. Then we divide each one. So this one is simply 20 divided by 19,383. Then for the rest is the same. So 72 divided by 19,383 is this one. So we calculate the relative frequency. Then we make graph, right? 0 to up to 20. Up to 27. So this is the 27, the last, and this is the 0. Then we make some bin or intervals, right? For example, 0 to 1, 1 to 2, 2 to 3, this one. And the relative frequency is here. We can go. Normally, it should be 1. It should not be more than 1. But this small number here, because we round up. That's why you can see here. But it should be 1. And in terms of percentage, it should be 100%. Either from the tabulated information or from the histogram itself, we can determine the proportion of games with at most 2 hits and the proportion of games with between 5 to 10 hits. So the problem is here, what is the proportion of game with at most 2 hits? At most 2 hits, it means 0 hit, 1 hit, and 2 hit, right? So up to here. So what we do here, this one, this number, and this number, you sum up together and you will get this one. Then what is the proportion of games with between 5 and 10? Between 5 and 10, right? So this is 5 and this is 10. So we will get some of these and you will see this sum is here. So the proportion of games between 5 to 10 hits is 0.6361. Inclusive means 5 and 10 also included. For continuous data, a histogram is used to display the distribution of values that are grouped into intervals or classes. These intervals or bins or classes represent range of values, and the width of each interval is equal, meaning each class contains the same range of data values. So how to do it? First, we determine the frequency and relative frequency for each class. Then we mark the class boundaries on a horizontal as the x-axis. Then above each class, we draw the rectangle whose height is corresponding to relative frequency. Here is an example. Power companies need information about customer usage to obtain accurate forecast of demand. Investigators from Wisconsin Power and Light determine energy consumption during a particular period for a sample of 90 gas-heated homes. And adjusted consumption value was calculated as adjusted consumption means consumption divided by weather in degree days house area. Then anyway, we have 90 data here. Now we want to plot the histogram. So here is our data set. So we have made some classes: 1 to 3, 3 to 5, 5 to 7, 7 to 9, 9 to 11, 11 to 13, 13 to 15, 15 to 17, and so on. These are our classes, okay, or intervals. Then we count. So between 1 and 3, how many we have? So we have only 1, right? I think this is the one that we have. Then we count for 3 to 5. You can see this one. From 5 to 7. 5 to 7. 5 to 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so on. Then we find out the relative frequency. What is the relative frequency? Total, that is 90, and 1 by 90. Okay. Then 1 by 90, 11 by 90, 21 by 90. Then we go for histogram. So histogram, here are our interval: 1 to 3, 3 to 5, 5 to 7, 7 to 9, up to 17 to 19, right? So relative frequency is what? This one multiply 100. This one multiply 100. So 0.11 divided by 100 is equal to 1%. So you can see 1% here, 1% here, then we have 11% here. So let's find the proportion of observation for less than 9. Less than 9. Less than 9, it means what? Less than 9, it means here. So the sum of this one. These are less than 9, right? So 0.011, 0.011, this one, then together, right? What is this one? The total here, the total is 1 plus 1, 2, and 11, 13, 21, 34, divided by 90. So 34 divided by 90 is this one. What is the proportional observation of less than 10? Less than 10, again, we will do the same. Less than 10 will be something here. Something here, right? Again, we will count and we will calculate, then we will come up with this one. It's very easy. So we need to make a histogram for continuous data when the class width are unequal. In here, these are equal, right? So we say 1, 2, 3, 2, 3 to 5. So this increased by 2, but sometimes it is not like that. You know, these are unequal class width. First, we need to determine the frequency and relative frequency for each class. The frequency, as I said, is the data points falling within the class. Once we have the relative frequency, we calculate the height of each rectangle in our histogram, and this is called as density. So density is relative frequency of the class divided by class width, right? Density, or rectangle height that we want to show it. This adjustment ensures that the area of each rectangle accurately represents the proportion of data in that class. So this is for the cases where class widths are unequal. So let's see one example. Here, corrosion of reinforcing steel is a serious problem in concrete structure located in environments affected by severe weather conditions. For this reason, researchers have been investigating the use of reinforcing bars made of composite material. One study was carried out to develop guidelines for bonding glass fiber reinforced plastic rebars to concrete. Anyway, these are data. Based on that, we will calculate, right? So we have classes 2 to 4, 4 to 6, 6 to 8, 8 to 12. You can see they are not the same. So the width is 2, 2, 2. Here is 4. Here is 8. Here is 10. You can see. So again, we calculate, we find out the numbers in each class. Then we go for relative frequency, and then we calculate the density. How to calculate the density? Is equal to relative frequency of the class divided by class width. Okay, so relative frequency is what? 0.1875 divided by 2 is 0.094. This one, 0.3125 divided by 2 is this one. This one divided by 4. So 0.1875 divided by 4. This one divided by 8. And then we can go for here. So you can see unequal classes, you can see here, and this is density. The first density is 0.94. The second density is 156. And the rest you can see. This is called as density. Both frequency distribution and a histogram can be constructed when the data is qualitative, categorical in nature. In some cases, there will be a natural ordering of classes. For example, we say freshmen, sophomores, juniors, seniors, and graduate students. The Public Policy Institute of California carried out a telephone survey of 2,501 Californian adult residents during April 2006 to ascertain how they felt about various aspects of K-12 public education. One question asked was, overall, how would you rate the quality of public schools in your neighborhood today? Anyway, the rating was A, B, C, D, E, F, don't know. How many people say 4, 7, 8 people say A, 8, 9, 3 people say B, and so on. The sum of people is here. Then we'll calculate the relative frequency. What is the relative frequency? 4, 7, 8 divided by 2,501 is equal to 0.11. Okay, so we calculate here and you can see the sum is 1. Okay, then we can go for histogram. You can see A and it is 191.191. This one B, it is 0.357, and the rest you can see. So this is histogram. So from this histogram, we can understand that more than half the respondents gave A or B rating. A or B rating, and only slightly more than 10% gave D or F. Visual summaries of data are excellent tools for taking preliminary impression and insights. More formal data analysis often require the calculation and interpretation of numerical summaries measures. That is, from the data, we try to extract several summarizing numbers that might serve to characterize the data set and convey some of its salient features. Consider a data set of x1, x2 up to xn, and in here, each xi is a number. What features of such set of numbers are most interesting and deserve emphasis? One important characteristic of a set number is the location, and in particular, its center. So we can say this is as mean, or you can say average. Average is sum of all numbers, as you can see here, sum of I from 1 to n. You can see here, I is 1 here and n is here. Divided by n. N is what? The total number of numbers. You can see n is here. So in this way, we can calculate the mean. Consider this data set. We have some values. How many values? 14. So n is equal to 14. Then we want to calculate the mean. Very easy, right? We will sum up them together. It means 16 plus 30.5 plus 70.7 up to 6 divided by n. N is 14. So the mean or average is 16.36. And you can see here, it is here. Similarly, the population mean is the average of all values in our population. So you can go for this one, mu, the average of all values in population, sum of all population. What is the difference between population? Population is all the data set that we have. Sample is some subset of the data set that we have. So n is the number of values in our population, a finite population. Median, if we sort the data, then we can find the middle value as the median. So this is considered as the middle value of a sorted data. So two ways are there here. If we have odd number of values, if mean n is odd, then simply we can go for n plus 1 divided by 2 and we get it, right? But if it is even, So we don't have any center value. So we go for n divided by 2 plus n divided by 2 plus 1 and then divided by 2. Then it means we find the average number. For example, if we have 3, 5, 6, 7, 9, in this case, median is 6 because this is the mid one, right? So what is n here? 1, 2, 3, 4, 5. So for here, we say 5 plus 1 divided by 2 is third. So the third is median. But another case is that the number of values is even. For example, we have 3, 5, 9, and 10. In this case, there is no median here. So what we do here, this is 1, 2, 3, 4. What we do here, we say 4 divided by 2 is equal to what? 2. So we get this one and this one. So we will have 5 plus 9 divided by 2 is 7. So the median for here is 7. So you can see this data set here. In this data set, how many numbers we have? 12. We don't have any single value as the middle one. So we calculate the average of the two middle one. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So we will calculate sum of these two divided by 2. Then we say the median is 66.9. The next item in the measure of locations is quartile. And also we have something called as trim mean. Quartile divide the data set into 4 equal parts. The first 25%, the second 25%, third 25%, fourth 25%. So here you can say from 0 to 25, then from 25 plus to 50, from 50 plus to 75, and 75 to 100. These are called as quartile. Also, they are known as Q1, Q2, Q3, and Q4. The next one is trimmed mean. Trimmed mean is also another statistical measure of central tendency. It is calculated by removing a certain percentage of the smallest and largest value from a data set. Then we will calculate the mean. This method reduces the influence of outlier or extreme values and making the trim mean a more robust measure of the central tendency compared to the regular arithmetic mean that we have. So for this one, first we have to sort the data, then we determine the percentage to the trim, then remove the outliers, then we calculate the mean. So I will show you one example here. So let's see this example. How many numbers we have here? Total, we have 26 numbers here. So we will calculate the mean. Okay, it means sum of all divided by 26 is 3.65. Then median, again, we will go for the 13th and 14th, right? So this is 13th and this is 14th, sum together, then divided by 2, this one. For the trimmed mean, we calculate by removing a certain percentage of the smallest and largest value, then we will calculate. So here we have 26, okay? So 10% of 26 will be 2.6, so it means 2. We will remove 2 from up and 2 from down. So we approximately remove the lowest 2 and the highest 2 value. Then it trim mean, the trimming percentage of this one that we calculate, just x bar tr 7.7. 7.7 comes from here. Then we say it's equal to 3.42. It means we have removed these 2 and also we remove these 2. Then we calculated the mean. How we decide that 2 should be removed? Because we want to get 10%, right? So these 2 will get out. The next one is range as the measure of variability for sample data. The simplest measure of variability in a sample is range. It is the difference between the largest and the smallest value. This is the difference between the largest and smallest value. In this figure, we have 3 data, right? Data number 1, data number 2, and data number 3. So these are 3 samples. The value of the range from sample 1 is much larger than the sample of, because the range of the 3 is this much, but the range of the 1 and 2 is this much, right? So this reflects more variability in the sample number 1 compared to the sample number 3. The defect of the range, though, is it depends only on 2 most extreme observations and disregard the position of the remaining data here, okay? For example, even though these 1 and 2 have the same range, they have identical range, yet when we take into account the observation between the 2 extremes, there is much less variability or dispersion in the 2 compared to 1. So our primary measure of variability involves the deviation from the mean. That is, the deviation from the mean are obtained by subtracting the average from each of the n-sample observations that we have. So a deviation will be positive if the observation is larger than mean. It means to the right of the mean on the measurement axis, and the deviation will be negative if the observation is smaller than mean. And if all deviations are small in magnitude, then all xi's are close to the mean and there is little variability. So we go for the next one, sample variance. Sample variance we show by S square. This is the measure of how much the data points in a sample deviate from the sample mean. How do we calculate? Xi, each data point, minus average of them squared, then sum up together, divided by n minus 1. N minus the number of observation that we have, minus 1. Okay. Then we have sample standard deviation. Just square root of variance is sample standard deviation. This sample standard deviation is measures the spread of data points in a sample. So these two are non-negative. S2 is always greater than 0 and S is also greater or equal to 0. Here is an example. We want to calculate the variance and standard deviation. So what we do here, these are our data, 1 to 11 that we have, then x minus x bar. So what is the average of this one? We will calculate the average of this data set. Then every point minus the average. Average is 33.26. So 27.3 minus 33.26 is equal to this one. Again, this one, 27.9 minus 33.26 is this one. Then we will do for all. Then we will calculate this one and sum up. Then we will square this one square. It means minus 5.96 square is equal to 35,522. Then this one the same. Then we can calculate S2, right? What is S2? This one 314.106 divided by how many numbers do we have? 11. 11 minus 1, then we have, so the variance is 31.41. Then what is the S? S is this one square root. So 31.41 is equal to 5.6. This is how we can calculate S2 and S. So in the previous slide, we said sample variance. Sample, it means a sample of all the data that we have. If you want to go for all the data, in this case, we will consider all number of data. So we show it by sigma squared. The variance of population is shown by sigma squared, and it measures how much each data point in an entire population deviates from the population mean. So we have xi as the individual data points, then we have mu as the average or mean of the population, and n is the total number of data points in our population. Then we can square root of sigma squared is equal to sigma as the population standard deviation. So population we can calculate in this way. So if you remember, we say for the calculation of sample, we say n minus 1. But in here, we didn't say n minus 1. The sample variance is divided by n minus 1. Why? Because the sample mean underestimates variability. So it requires some correction. That's why we say n minus 1. This is also known as Bezel's correction. So let's see one example. Consider this data set is very easy data set. We want to calculate the S and S square. So this is our data set. Sum of them together 1695. Then each one is square. It means this one is square, this one is square, up to then we will have this number. Then xi minus x bar square divided by n minus 2. Okay, it means each one minus the average. It means this one divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So then n minus 1 divided by 12, we will get this number. Then this number divided by 12 is equal to 131.9. So this is how we calculate. Again, I will explain. We need this value, right? So for this one, we will say xi, this one, 154 minus this one. What is the value for this? So here we calculate the x bar, which is 1695 divided by 13, which is 1.38. Okay, then this one minus 130.38 square plus the second one 142 minus 130.38 square. Then we will sum up them all together. We will come to this number. Then this number divided by n minus 1. N is 13 minus 1, 12. Then we will get this one as the variance. And this one square, it means root square of 131.59 is equal to 1147. This is the standard deviation. Next, we go for box plots. So box plots is used for describing several of data set most prominent features, including center of our data set, spread of data set, the extent and the nature of any departure from symmetry, and also identification of outliers. In one example, already you see what is outlier. Observations that lie unusually far from the mean body of the data, either too small or too big from the mean. Then we go for a fourth spread. This is a measure spread resist to outliers, and we calculate fs upper fourth minus lower fourth. What is lower fourth? The median of the smallest half, and the upper fourth is the median of the largest half. So to do that, we need to order the n observation from smallest to largest, and then separate the smallest half from the largest half. The median is included in both halves if it is odd. We have odd number of values. The simplest box plot is based on 5 number summary. Smallest xi, lower fourth, median, upper fourth, and large. If you have this one, then we can go for a box plot. First, we draw a horizontal measurement scale. Then we place a rectangle above this axis. The left edge of rectangle is at the lower fourth, and the right edge is at the upper fourth. Then we place a vertical line segment or some other symbol inside the rectangle at the location of the median. The position of the median symbol relative to the two edges conveys information about the skewness in the middle 50% of data. Finally, we draw V-squares out from either end of the rectangle to smallest and largest observation. So here we can see one example. This is our data set. And how many numbers do we have? 40. What is the mean? 6.2. This SE mean, This is considered a standard error of the mean, and it is S divided by n, standard deviation by root square of the number that we have. Then we have standard deviation based on the equation that we have: minimum, Q1, median, Q3, and maximum. So this has the dot plot that we have for our numbers. You can see here, most of the data are here, and these are considered as somehow outliers. Both plots indicate that there is a reasonable amount of symmetry in the middle of 50% of the data, but overall values stretch out more toward the low end than toward the high end. It means we have a negative skew. So the box itself is not very narrow, indicating a fair amount of variability in the middle half of the data. So I told about outliers. Outliers is any observation farther than 1 point fs from the closest source. We have also something called as extreme outlier. It means any observation which is more than 3 fs from the nearest source. What is fs? Upper force minus lower force. Okay, thank you guys for attention. I hope you understand the topic. Surely we will exercise more, we will do coding, and also in class we will study more about the topics that we learned in this video lecture. Please feel free to ask me if you have any questions. Thank you.